Have you ever wondered what secrets the Milky Way is hiding? What lies beyond that soft, glowing band of stars that stretches across the night sky? Welcome to Facts for Sleep, the place where curiosity meets calm. In tonight's video, you're invited on a peaceful journey through the galaxy we call home. You'll discover fascinating truths about the Milky Way, from its ancient origins to the mysterious forces that shape it and the countless stars and planets it holds, all while slowly drifting into rest, guided by the gentle hum of 432 Hz music, chosen to soothe your mind and body. This isn't just a list of facts, it's an experience, a calm exploration of a vast and beautiful place, woven with wonder and designed to ease you into sleep. To help your imagination come alive, every image in this video has been created using artificial intelligence. These visuals are not only meant to be beautiful, but also educational, giving you a clearer sense of what our galaxy might truly look like. Think of them as dreamscapes, gentle windows into a universe that's both real and magical. If this is your first time here, welcome. We're glad you found us. If you enjoy this journey, consider subscribing to support the channel and to join us again on future explorations, each one designed to calm your thoughts, satisfy your curiosity, and help you sleep just a little deeper. Thank you for being here. Now, let the music begin, the stars guide you, and may your dreams take you far beyond. Let's begin. The Milky Way looks like a quiet band of light, but it is actually the view from inside a gigantic spiral galaxy. When you see that pale river across the night sky, you are looking through a crowded disk packed with stars and dust. The glow is strongest because your eyes are pointed along the galaxy's plane, where star density is highest. Dark lanes cut through the light because clouds of dust block starlight like fog in a forest. To understand why the center looks even richer, we have to travel inward. If you could fly toward the middle, the sky would slowly fill with more stars than you can imagine. The galactic center is a bustling region where stars, gas, and dust swirl in tight orbits. Even through a telescope, much of it is hidden in visible light because dust absorbs it. That is why astronomers use longer wavelength light, like infrared, to peek through the haze. And when we finally see the heart clearly, we meet something even stranger. At the Milky Way's center sits a supermassive black hole called Sagittarius A star. It is about 4 million times the mass of the Sun, yet it fits into a region smaller than our solar system. Stars near it whip around at incredible speeds, revealing the black hole's gravity even though it is invisible. When gas falls in, it can glow intensely before disappearing like sparks around a drain. To appreciate how far we are from that powerhouse, we should locate our own neighborhood. Our solar system lives in a spiral arm region, often called the Orion Arm, tucked between larger arms. We are not near the center, and we are not near the edge either, which is lucky for long-term stability. It takes roughly 225 million years for the Sun to complete one orbit around the galaxy. That means dinosaurs lived under a sky where our Sun was in a different part of its galactic journey. Next, let's imagine what that orbit really looks like. The Sun does not travel in a perfect circle around the galactic center. Its path gently wobbles up and down through the galactic disk like a horse on a carousel that also moves vertically. This motion can change how much interstellar dust surrounds us over time. Some researchers wonder whether these passages through denser regions could influence the solar system's environment. Whether or not that affects life, it shows the Milky Way is dynamic, not static. And that dynamism becomes even clearer when we talk about the galaxy's true size. The Milky Way is so wide that light, the fastest thing we know, needs about 100,000 years to cross its main stellar disk. That distance is hard to feel because everything in daily life is tiny by comparison. If the solar system were a coin, the Milky Way would be larger than a continent in that scale. Yet the galaxy is not a solid object. It is mostly empty space between stars. To see what holds that vast structure together, we have to talk about the invisible mass. Most of the Milky Way's mass is thought to be in a halo of dark matter that does not emit light. We know it is there because stars orbit too fast for the visible matter alone to provide enough gravity. This dark matter halo extends far beyond the bright disk, like an unseen cocoon. Without it, the Milky Way might not hold together in its current form. And once you picture this hidden halo, it makes the galaxy's shape even more interesting. The Milky Way is often described as a spiral galaxy, but it also has a central bar of stars. That bar acts like a cosmic stirrer, guiding gas inward and shaping the spiral arms. Many spiral galaxies have bars, and they can influence where new stars form. If you could see the Milky Way from above, the bar would look like a bright line across the center. Following that line naturally leads us to the spiral arms themselves. Spiral arms are not rigid spokes made of the same stars forever. They are more like traffic jams in space, where stars and gas bunch up as they orbit. When gas gets compressed in these denser regions, it can collapse and form new stars. That is why spiral arms often shine with clusters of young, bright stars. To see star birth up close, we should zoom in on the galaxy's nurseries. The Milky Way contains enormous star-forming clouds called nebulae, where new suns ignite. Inside these clouds, gravity pulls gas into dense knots, heating them until nuclear fusion begins. Many newborn stars form in groups, like siblings in a crowded nursery. Their intense light can carve cavities in the surrounding cloud, creating glowing shapes and pillars. Those newborn stars set the stage for the next surprise, because stars do not always live in peace. Some stars are born as pairs, or even as triples, orbiting one another for billions of years. In these systems, one star can steal gas from its partner if they are close enough. That theft can cause dramatic outbursts, and in certain cases, it can trigger a supernova explosion. The Milky Way is filled with these intimate stellar relationships, each one a natural laboratory for extreme physics. And supernovae are the perfect doorway into the story of how the galaxy builds elements. When a massive star explodes as a supernova, it forges and flings heavy elements into space. Many of the atoms in your body, like iron in your blood, were made in stars and delivered by such explosions. Over time, these enriched materials mix into new clouds that form new stars and planets. In a real sense, the Milky Way is a recycling machine that turns stardust into worlds. That raises an obvious question. How often does the recycling explode right near us? Supernovae in the Milky Way are rare on a human timescale, but common on a cosmic one. A typical estimate is a few per century somewhere in the galaxy, though dust can hide many from our view. When one happens nearby, it would be an unforgettable sight, bright enough to cast shadows at night. Thankfully, truly dangerous nearby supernovae are much less frequent. Still, even without explosions in our backyard, the Milky Way is full of energetic radiation, so let's talk about cosmic rays. Cosmic rays are high-energy particles that zip through the galaxy at near light speed. Many are launched by shock waves from supernova remnants, like debris accelerated by an expanding blast. When these particles hit Earth's atmosphere, they create showers of secondary particles, a constant invisible rain. The Milky Way is therefore not just a collection of stars, but also a sea of fast-moving particles. And if particles can travel, so can entire stars, which brings us to stellar migration. Stars do not always stay where they were born. Over time, gravitational nudges from spiral arms, the central bar, and passing clouds can shift a star's orbit. This process can move stars inward or outward across the disk, mixing the galaxy like a slow cosmic blender. The Sun itself may have drifted from its birthplace, though the details are still debated. That mixing sets up another mystery, because not all stars in the Milky Way are the same age. The Milky Way contains very old stars that formed near the beginning of the galaxy's history. Some of these ancient stars have very low amounts of heavy elements, hinting they were born before many generations of supernovae enriched the gas. Studying them is like reading the first chapters of the Milky Way's origin story. They often live in the halo or in dense clusters, far from the spiral arms. Those clusters are a fascinating next stop because they are like cities of stars. Globular clusters are tightly packed balls containing hundreds of thousands of stars. Many orbit the Milky Way in the halo, like lanterns surrounding the main disk. Their stars are generally old, and their crowded centers can create unusual interactions. In such dense environments, stars can exchange partners or collide, producing exotic objects. And among those exotic objects, we find some of the strangest clocks in the galaxy. Pulsars are rapidly spinning neutron stars, the dense leftovers of massive stars. They beam radiation like lighthouse lights, and as they spin, the beam sweeps past Earth in steady pulses. Some pulsars are so precise that they rival atomic clocks, keeping time over years with astonishing stability. In the Milky Way, pulsars help us map gas, test gravity, and measure the galaxy's magnetic field. To understand what they are left behind from, we should briefly face the extreme of neutron stars themselves. A neutron star packs more mass than the Sun into a sphere about the size of a city. A teaspoon of its matter would weigh billions of tons on Earth, far beyond everyday intuition. Its gravity is so strong that standing on its surface would pull you down with a force that would crush anything normal. Yet neutron stars can be born spinning and magnetized so intensely that they become cosmic dynamos. That naturally leads us to magnetars, which are neutron stars turned up to 11. Magnetars have magnetic fields so powerful they can distort atoms. If one were close enough, it could disrupt electronics even from far away, which sounds like science fiction, but follows from real physics. Magnetars occasionally release bursts of high-energy radiation, bright enough to be detected across the galaxy. These eruptions remind us that the Milky Way is not only beautiful, but also violent. And violence is not limited to stars, because the galaxy also hosts a zoo of smaller wanderers. Between the stars, the Milky Way contains countless comets, asteroids, and rogue planets. Rogue planets may drift through interstellar space without orbiting any star, possibly ejected during the chaos of planet formation. They would be almost invisible unless they pass in front of a star and briefly bend its light. If there are many, the galaxy could be filled with dark worlds quietly wandering the night. That idea points us toward how astronomers weigh and map what they cannot see directly. We can map parts of the Milky Way by tracking how gas clouds move and how their light shifts. Radio astronomy is especially useful because radio waves pass through dust that blocks visible light. By studying the emission from hydrogen gas, astronomers can trace spiral structure across large distances. This is how we learned that our view from inside is biased and incomplete, like trying to map a forest while standing under the trees. With that challenge in mind, the next fact is about a clever trick the galaxy provides for measuring distance. Certain stars act as standard candles, meaning their true brightness can be inferred from their behavior. Cepheid variable stars brighten and dim in a regular way that reveals their intrinsic luminosity. By comparing that true brightness with how faint they appear, we can estimate their distance. This method helped us place key parts of the Milky Way structure and calibrate larger cosmic distances. Once you can measure distances, you can also ask how many stars the Milky Way contains. The Milky Way likely contains hundreds of billions of stars, though the exact number is uncertain. Many are small red dwarfs that are too dim to see easily at great distances. That means the galaxy is probably even more crowded than the night sky suggests. If most stars are faint, then many potential planetary systems could be hidden in plain sight. And with planets in mind, we arrive at one of the biggest hooks of all. How many worlds might be out there? The Milky Way appears to host an enormous number of planets, likely in the hundreds of billions. Exoplanet surveys suggest planets are common around many types of stars, including small ones. Some systems have tightly packed planets that orbit closer to their stars than Mercury orbits the Sun. Others have giant planets far out, shaping belts of icy debris. If planets are common, then habitable zones and the possibility of life become a natural next step. A star's habitable zone is the region where temperatures could allow liquid water on a rocky planet's surface. In the Milky Way, this zone depends on the star's brightness, so around small stars it lies much closer in. That closeness can create challenges like strong stellar flares or tidal locking, where one side always faces the star. Yet life, if it exists, might adapt in ways we have not imagined. To broaden the view, we can zoom out to the idea of a galactic habitable zone. Some scientists propose the Milky Way has a galactic habitable zone, regions more favorable for long-term complex life. Too close to the center, radiation and crowded stellar neighborhoods may increase risks from supernovae or gravitational disturbances. Too far out, there might be fewer heavy elements needed to form rocky planets. Our position is sometimes described as a sweet spot, though the full picture is still uncertain. This naturally leads to a curious thought. The galaxy might be full of life and yet feel silent. The so-called Fermi paradox captures that tension between the galaxy's vast potential and the lack of clear evidence of other civilizations. If the Milky Way has billions of planets, why do we not see obvious signs of widespread technology? Many explanations exist, ranging from the difficulty of life arising to the possibility that signals are brief or hard to detect. The silence could also be a limitation of our search methods, not proof of absence. Thinking about detection brings us to the ways the Milky Way itself can interfere with our signals. Interstellar dust and gas can scatter and absorb certain kinds of light, hiding regions of the galaxy. This is why a radio telescope can reveal structures that an optical telescope cannot. Even signals from faraway civilizations, if they exist, might be distorted by the interstellar medium. The Milky Way is not an empty vacuum. It is a complex environment that shapes what we can observe. And that environment becomes spectacularly visible when we talk about the galaxy's giant bubbles and arcs. Astronomers have found huge structures in and above the Milky Way, like vast lobes of high-energy emission extending from the central region. These features hint at past outbursts from the galactic center or waves of intense star formation. They show that Sagittarius A star and its surroundings may have been more active in the past. The Milky Way we see today may be in a calmer phase of a much more dramatic history. And to uncover that history, the next facts should follow the galaxy's past collisions and future fate. The Milky Way did not grow alone. It grew by swallowing smaller galaxies over billions of years. When a dwarf galaxy drifts too close, the Milky Way's gravity stretches it into long streams of stars. Those streams can wrap around our galaxy like ribbons, leaving clues about ancient mergers. Some of the stars in our halo may have originated in galaxies that no longer exist as separate objects. In that sense, the Milky Way is part original and part cosmic collection. One of the clearest ribbons leads us to a famous ongoing merger. The Sagittarius dwarf spheroidal galaxy is being torn apart right now as it orbits the Milky Way. Its stars are being pulled into vast tidal streams that arc across the sky. These streams act like footprints, showing where the dwarf has traveled and how gravity shapes its path. By mapping them, astronomers learn about the Milky Way's mass and the shape of its dark matter halo. This is a rare chance to watch galactic growth in real time, and it is not the only neighbor interacting with us. The Milky Way's two most famous companion galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud. They are visible from the southern hemisphere as cloudy patches, which is how they got their name. These companions tug on the Milky Way and on each other, stirring gas and triggering bursts of star formation. Their motions also help astronomers estimate how massive the Milky Way must be to keep them nearby. Even our galaxy's disk may be slightly warped because of such gravitational nudges. That warp is the perfect next thing to picture. The Milky Way's disk is not perfectly flat. It is subtly bent and rippled like a record left in the sun. This warp becomes more pronounced in the outer regions, where the galaxy's gravitational grip is weaker. Interactions with companion galaxies and with the dark matter halo can create these distortions. When you imagine the Milky Way from the side, it looks less like a neat pancake and more like a flexible sheet. These ripples tell us the galaxy is still settling and responding to its surroundings. If the disk can warp, it can also shake. Astronomers have found wave-like patterns in the Milky Way's stars that suggest the disk has been ringing from past encounters. A passing dwarf galaxy can act like a stone dropped into a pond, sending ripples through the stellar distribution. These ripples can persist for a long time, giving us a fossil record of gravitational disturbances. By measuring them, scientists can rewind the story to infer which objects may have passed through. This is galactic archaeology written in motion, not in bones. Next, we follow another signature of motion, the galaxy's rotation itself. The Milky Way rotates, but different parts rotate at different speeds. Inner regions orbit faster because they are closer to the massive center, while outer regions would slow down if only visible matter mattered. Instead, the rotation stays unexpectedly high, far out, one of the strongest hints for dark matter. This flat rotation curve is like a speedometer reading that refuses to drop when it should. It is a clue that most of the galaxy's mass is hidden from sight. And once you accept that, you start wondering what the Milky Way's true boundary even is. The bright disk is only the most visible part of the Milky Way. Beyond it lies a vast halo of stars, globular clusters, hot gas, and the dominant dark matter halo. Some estimates suggest the Milky Way's gravitational influence extends hundreds of thousands of light years out. That means our galaxy's territory in space is far larger than the luminous band we see. In a way, the Milky Way is an empire whose borders are defined by gravity, not light. Those borders matter a lot when we talk about the galaxy's biggest future meeting. The Milky Way and the Andromeda Galaxy are moving toward each other and will likely collide in the far future. This will not be a crash of stars like billiard balls because stars are extremely far apart, but it will be a dramatic gravitational dance. Over time, their shapes will distort, their gas will compress, and new waves of star formation may ignite. Eventually, the two galaxies may merge into one larger galaxy with a new structure. If any future humans exist then, their night sky would slowly transform over millions of years. But before that grand event, we should notice that the Milky Way is already connected to its neighbors in a subtler way. Between the Milky Way and Andromeda lies the local group, a small community of dozens of galaxies bound together by gravity. The Milky Way and Andromeda are the two heavyweights, while smaller galaxies orbit them like moths around porch lights. The local group itself is drifting through the larger cosmic web of matter. Thinking in groups helps us realize galaxies are social, constantly influencing one another. Even our Milky Way star formation rate can be shaped by these relationships. That brings us to a key question. How active is our galaxy at making new stars right now? The Milky Way forms new stars, but it is not in a frantic starburst phase. It converts gas into stars at a moderate pace, producing a few new stars each year on average. This may sound small, but across billions of years, it builds a staggering population. The rate depends on how much cold gas is available and how turbulence, magnetic fields, and gravity compete in giant clouds. In some regions, feedback from young stars can shut down further formation by blasting gas away. To see this tug of war, we should step into the thin space between stars. The space between stars is filled with the interstellar medium, a mix of gas, dust, and cosmic rays. It is not uniform. It ranges from cold, dense clouds to hot, thin bubbles carved by supernovae. Dust grains, though tiny, play a huge role by helping molecules form and by blocking and scattering starlight. This medium is the stage on which stars are born and die, constantly reshaping the galaxy's appearance. When you look at the Milky Way's dark lanes, you are seeing this medium in silhouette. And inside it, something surprising happens: chemistry. Interstellar clouds can host complex molecules, including organic compounds that are building blocks for life. These molecules form on dust grain surfaces and in gas phase reactions under extreme conditions. Radio telescopes can detect their signatures as distinctive patterns in frequency space, like molecular fingerprints. It means that the raw ingredients of biology are not unique to Earth. They are part of the galaxy's normal chemistry. In a sense, the Milky Way is preloaded with potential. That potential becomes even more dramatic when clouds collapse to form planetary systems. When a star is born, it is often surrounded by a rotating disk of gas and dust. Within this protoplanetary disk, particles collide and stick. building from grains to pebbles to planetesimals. Over time, gravity turns these building blocks into planets, moons, and asteroid belts. Meanwhile, the young star can blow winds and jets that sculpt the disk's structure. Our own solar system formed this way, inside the Milky Way's ongoing cycle. To understand how common our story is, we look at the most common kind of star in the galaxy. Red dwarf stars are the most numerous stars in the Milky Way. They are smaller and dimmer than the Sun, but they burn fuel slowly and can live for trillions of years. That means many planets around red dwarfs may have enormous windows of time for potential evolution. However, red dwarfs can be magnetically active, especially when young, producing flares that bathe nearby planets in radiation. Whether life can thrive, there is an open question, but the opportunity scale is enormous. And if we want to find such planets, the Milky Way gives us a clever method: gravitational microlensing. Gravitational microlensing happens when a star or planet passes in front of a more distant star and bends its light. The background star temporarily brightens in a characteristic way, revealing the presence of the lensing object. This technique can detect planets that are far from their stars and even objects that have no star at all. It is like seeing an invisible traveler because it briefly distorts a streetlight behind it. Microlensing events are rare and unpredictable, but they open a window onto hidden populations. Hidden populations matter even more when we consider the Milky Way's crowded core. The galactic bulge is a dense region of stars around the center, shaped in a slightly boxy or peanut-like form. It contains many older stars and is packed enough that the sky there would look dazzling to human eyes. Yet the bulge is not just a simple blob. It has structure tied to the galaxy's bar and past evolution. Studying it helps astronomers understand how the Milky Way assembled its inner components. Even though it is crowded, it can still host planets, though environments there may be more chaotic. That chaos brings us naturally to the problem of stellar encounters. In denser regions of the Milky Way, stars pass closer to one another more often. Close passes can disturb outer comet clouds and alter distant orbits in planetary systems. In extreme cases, they could strip planets away or destabilize the architecture of a system. Our neighborhood is relatively calm, which may have helped Earth remain stable long enough for complex life. It is a reminder that location in the galaxy can shape destiny. But even in calm regions, there are travelers from elsewhere. Some objects in our solar system may have originated outside the Milky Way's local neighborhood, or even outside the solar system entirely. Interstellar visitors, like certain fast-moving objects, show that material can wander between star systems. Such visitors offer a direct sample of other regions' chemistry and formation history. They also hint that planetary systems may exchange debris more often than we once thought. The Milky Way might be quietly mixing its ingredients across vast distances. And speaking of mixing, the galaxy also mixes time, because we can see different eras at once. When we observe faraway parts of the Milky Way, we are seeing them as they were thousands or tens of thousands of years ago. Light takes time to travel, so the galaxy is a mosaic of different moments. The center we see tonight is the center from about 26,000 years in the past, because that is roughly our distance to it in light years. This time delay is small compared to galactic evolution, but huge compared to human history. It is like looking at an old photograph that is still arriving. That idea sets up an even stranger point. Our view is incomplete and biased. From inside the Milky Way, we cannot easily photograph the whole galaxy the way we can with distant galaxies. Dust blocks many lines of sight, and perspective makes structure harder to infer. That is why maps of the Milky Way are partly reconstructed from motion, distance estimates, and multi-wavelength observations. It is like trying to draw a city map while walking through its streets in thick fog. Every improvement in measurement sharpens the picture. One of the biggest improvements came from an ambitious mission that measured stars with extraordinary precision. The Gaia space mission has been mapping positions and motions of a vast number of stars. With its data, astronomers can trace the Milky Way's structure in unprecedented detail, including streams from ancient mergers. By measuring tiny shifts in a star's position over time, Gaia reveals how it moves through the galaxy. This lets scientists identify families of stars that share a common origin, even if they are now widely separated. It transforms the Milky Way from a blurry concept into a detailed living map. That map reveals something curious. The galaxy has substructures like scars. Star streams are long, thin trails of stars that were once part of a globular cluster or a small galaxy. They form when tidal forces pull a system apart, leaving a stretched path along its orbit. Because streams are sensitive to gravity, they can reveal lumps and clumps in the dark matter distribution. If dark matter has small-scale structure, streams may show gaps or wiggles. In this way, streams act like ink lines that expose invisible fingerprints. And invisible fingerprints bring us right back to the galaxy's magnetic personality. The Milky Way has a magnetic field that threads through the disk and halo. It influences how cosmic rays travel and how gas clouds collapse into stars. Magnetic fields can shape the filaments we see in nebulae and can help launch jets from young stars. We cannot see the field directly, but we infer it from the polarization of light and the behavior of charged particles. It is like feeling wind by watching leaves move. Once you accept magnetism on galactic scales, you start noticing the galaxy also has weather. Galactic weather includes winds that blow gas out of the disk and fountains that cycle material up and down. Supernovae and intense star formation can drive hot gas upward into the halo, where it cools and falls back. This circulation helps regulate star formation by controlling how much cold gas remains available. It also spreads heavy elements across the galaxy, enriching future generations of stars. The Milky Way is therefore not a sealed system, it breathes. And where there is breathing, there is also feeding. The Milky Way is still accreting gas from its surroundings, pulling in material from the intergalactic medium and from smaller companions. This inflow provides fresh fuel for star formation over long periods. Without continued feeding, the galaxy would eventually run low on cold gas and star formation would fade. Some of this gas may arrive as high-velocity clouds moving through the halo at unusual speeds. These clouds are like deliveries arriving at the back door of the galaxy. If gas can fall in, it can also be thrown out, which leads to energetic outflows. Powerful events near the center and throughout the disk can launch outflows of gas. These outflows can carry energy and metals into the halo, changing the galaxy's environment. They also affect how the Milky Way interacts with its neighbors by extending its influence beyond the disk. Think of them as the galaxy's way of venting heat and pressure. This feedback loop is one reason galaxies do not turn all their gas into stars at once. And now that we have winds and fountains, we should look at what is floating in that halo. The Milky Way's halo contains hot gas that is difficult to see directly. It reveals itself through absorption lines in the light of distant sources and through faint X-ray emission. This halo may hold a significant fraction of the galaxy's ordinary matter, helping solve the puzzle of missing baryons. It is like discovering a huge reservoir around the galaxy that was invisible in ordinary photographs. The halo also acts as the medium through which satellites orbit and interact. And one satellite in particular is shaping our future, the Large Magellanic Cloud. The Large Magellanic Cloud may be on its first close approach to the Milky Way, depending on its past orbit. If so, its arrival is a relatively recent event in galactic terms, and its mass can significantly perturb our galaxy. It may influence the Milky Way's dark matter halo and contribute to the disk's warp. Its own star formation regions are among the most active nearby, offering a laboratory for how galaxies form stars. The interaction is like two dancers approaching, each changing the other's steps. That dance sets the stage for another intriguing concept, the Milky Way's family tree of stars. Astronomers can do stellar genealogy by comparing the chemical fingerprints of stars. Stars formed in the same cloud often share subtle patterns of elements, like a shared recipe. Even after the group disperses across the galaxy, that chemical signature can remain. This technique, called chemical tagging, can help reconstruct lost star clusters and ancient events. It is like identifying siblings separated at birth by matching their DNA. And the final push in this section is the biggest question that chemical history raises. How did the Milky Way begin? The Milky Way likely started as smaller clumps of gas and dark matter that merged in the early universe. Over time, gas cooled, formed a disk, and began sustained star formation, while mergers built up the halo. The galaxy's oldest stars carry the memory of those early conditions because they formed before the galaxy was fully mature. The structure we see now is the result of billions of years of growth, recycling, and interaction. In other words, the Milky Way is a long story written in starlight and gravity. If you could step far outside the Milky Way and look back, you would see a barred spiral galaxy with sweeping arms and a glowing core. The arms would shine with young stars, and the center would glow more golden due to older stars. From that vantage point, the galaxy would appear flat and majestic, like a cosmic pinwheel floating in the dark. Light from it would span about 1 degree in the sky, roughly twice the width of the full moon. It's the kind of view we can only imagine for now, but our imaginations sharpen with help from our neighbors. The Andromeda Galaxy gives us a clue about how the Milky Way might look from outside. As our nearest large galactic neighbor, Andromeda is visible with the naked eye from dark skies and shows a similar spiral structure. Photos of Andromeda taken with long exposure cameras often serve as a proxy for what our galaxy would look like to distant eyes. In truth, the Milky Way might be slightly more massive or slightly less luminous. It's hard to compare from inside, but imagining that view makes our own place feel even more real. And it raises the question, how do we actually see a galaxy we live inside. Our view of the Milky Way is a blend of observation and reconstruction, telescopes operating at different wavelengths. Optical, infrared, radio, X-ray reveal slices of its structure. Infrared helps us see through dust, radio maps cold gas, and X-rays uncover high-energy activity. Together, these data allow astronomers to build composite models of our galaxy's shape and behavior. It's like exploring a city using drone footage, weather sensors, and underground scans all at once. This multi-view approach leads us to one of the most detailed maps ever made. The European Space Agency's Gaia mission has measured the positions and motions of over 1 billion stars. With its data, astronomers can trace spiral arm patterns, star clusters, and stellar streams in unprecedented detail. Gaia even reveals subtle wobbles caused by unseen companions like exoplanets or black holes. The mission has revolutionized galactic cartography, turning our vague outline of the Milky Way into a dynamic, living map. That level of detail lets us discover not just where things are, but how they move. And sometimes we find things moving in surprising ways. Some stars in the Milky Way are traveling at speeds fast enough to escape its gravity. These hypervelocity stars may be the result of interactions with the supermassive black hole or collisions in dense clusters. A star ejected this way can become a rogue traveler, coasting alone through intergalactic space. Observing such stars is rare, but provides clues about extreme gravitational environments. It shows that while stars often orbit in harmony, the galaxy can also fling them out, and that makes us wonder what else the Milky Way might be ejecting. Besides stars, the Milky Way can launch hot gas and even entire star clusters into the halo. These ejections may be triggered by supernovae or bursts of activity near the galactic center. They contribute to a cycle where gas is pushed up, cools down, and sometimes rains back onto the disk. This galactic fountain keeps the ecosystem going, mixing elements across distances. It's like the galaxy has lungs that breathe gas in and out. That motion is beautiful, but sometimes it makes things go bump in the night sky. Occasionally, stars in our galaxy brighten dramatically and temporarily. These events are called novae. A nova typically occurs in a binary system where a white dwarf pulls gas from a companion star until a burst of fusion ignites. It's not as powerful as a supernova, but it can light up a patch of sky that was previously dark. These outbursts have been observed for centuries and were often seen as omens in ancient times. Today, we know they are part of the normal life cycle of stars, and the more we study stellar cycles, the more patterns we find. Some parts of the Milky Way pulse with regular rhythms thanks to variable stars. These stars expand and contract in size, causing changes in brightness that can be measured over days or weeks. Their patterns help astronomers measure distances and trace structure, especially in regions where other stars are hard to resolve. Variable stars act like blinking beacons, telling us how far we are from different parts of the galaxy. They are one of our oldest tools in the cosmic toolbox. And that toolbox has grown rapidly in the age of space telescopes. Space telescopes like Hubble, Spitzer, Chandra, and Gaia have allowed us to study the Milky Way across the full electromagnetic spectrum. Each one reveals something different. Hubble shows fine optical detail. Spitzer peered through dust in infrared. Chandra captured hot gas in X-rays. Together, they have uncovered star nurseries, black hole jets, and ancient remnants hidden from ground-based views. observing from space removes the blur and blockage of Earth's atmosphere. That clarity is crucial when you're peering into something as complex as a galaxy, and it lets us spot things we never expected. One of the surprises was the discovery of huge bubbles of high-energy radiation stretching above and below the Milky Way's center. These Fermi bubbles, named after the gamma-ray space telescope that found them, are relics of past energetic events. They may have been caused by a burst of activity from the central black hole or from waves of intense star formation. Either way, they are a reminder that the galaxy's history includes violent episodes we can still see the aftermath of today. These leftovers are cosmic clues, and they make us ask what else is lurking just out of sight. Deep in the disk and hidden by dust, astronomers recently discovered new spiral arm segments using radio telescopes. These newly found structures help refine our understanding of how the arms are arranged and how stars move within them. Some arms may split, fade, or twist rather than forming perfect textbook spirals. It's like finding new roads in a familiar city by looking at traffic patterns. Every new piece changes the map just a little, and once we map the arms, we can follow them to clusters of young stars lighting the way. Star clusters are groups of stars that formed from the same cloud of gas. Open clusters tend to be young and loosely bound, scattered across the spiral arms like glitter on a table. Over time, these clusters drift apart, but while they last, they help trace where recent star formation occurred. Some of the most famous star clusters, like the Pleiades, are visible to the naked eye. They are cosmic neighborhoods, shining bright before they slowly disperse. And as they disperse, they leave behind stars that may carry planetary systems with them. Many stars in the Milky Way have planetary systems, and the diversity of those systems is staggering. Some have hot Jupiters, giant planets close to their stars, while others have compact, rocky worlds packed into tight orbits. There are also planets in wide orbits, and even orphaned planets with no star at all. This diversity tells us that planet formation is both common and chaotic, and it deepens the mystery. How many of those planets might be like Earth? Earth-like planets are defined not just by size, but by location in the habitable zone, where liquid water could exist. The Milky Way likely contains billions of such worlds, though most are too distant or faint to study in detail. Future telescopes may be able to analyze the atmospheres of these planets and look for chemical signs of life. Until then, they remain tantalizing possibilities, a quiet ocean under a foreign sky. Thinking about life leads naturally to the question of whether anyone else might be out there, looking back. The search for extraterrestrial intelligence, SETI, scans the Milky Way for unusual radio signals or light patterns. The idea is that an advanced civilization might produce detectable technology, even if we never meet them. So far, no definitive signals have been found, but the search continues with better tools and broader scopes. The silence may be meaningful, or it may be a matter of time and technique. Either way, the Milky Way remains the most promising place to look for cosmic company, and that search brings up a haunting realization. Even if other civilizations exist in the Milky Way, the vast distances between stars make contact incredibly difficult. Messages might take thousands of years to travel one way, and even light-speed probes would be agonizingly slow. That means the galaxy could be full of life, but so spread out that each species lives in solitude. It's a humbling thought, and one that makes our own planet feel even more precious. And speaking of our planet, let's remind ourselves of where it sits in all this. Earth orbits a modest star in a quiet corner of a spiral arm, about 26,000 light-years from the galactic center. It's a relatively calm place, away from the hazards of the core and rich enough in elements for life to emerge. Our Sun makes a full trip around the Milky Way every 225 million years, and Earth is riding along for the journey. That means everything that's ever happened here, from dinosaurs to smartphones, took place during a tiny sliver of one galactic orbit. That perspective reshapes time itself, and it shows how young we really are in galactic terms. The Milky Way is over 13 billion years old, more than 3 times the age of our solar system. It existed before Earth, before the Sun, before most of the elements that make up our bodies. Our star and planet formed in the wake of countless stellar deaths and rebirths, part of an ongoing cycle. In that sense, we are not just in the Milky Way, we are of it. Our atoms once lived in other stars, and someday they will return to the stars again. That cosmic recycling makes the next realization even more beautiful. When you look up at the Milky Way in a dark sky, you are seeing the glow of hundreds of billions of stars, woven together by gravity and time. Some of the light is ancient, some more recent, but all of it connects across unimaginable distances. It's easy to forget that you are inside one of those stars' planetary systems, peering out from within. We don't just observe the galaxy, we live inside it, like fish trying to map the ocean. And there's always more to discover in the deep. The Milky Way is not just a galaxy, it's our home, our history, and our launchpad to the universe. From dark matter halos to newborn stars, from rogue planets to ancient streams, it contains everything we know and so much we don't. Its beauty lies not only in its form, but in the questions it inspires. Every fact opens a door to another mystery. Every observation leads to another wonder. For thousands of years, people have looked up at the Milky Way and created stories to explain it. In many cultures, the band of light across the sky was seen as a river, a path, or a bridge between worlds. The ancient Greeks thought it was spilled milk from the goddess Hera, giving the galaxy its name. In some Native American traditions, it is the path of souls moving through the sky. These stories reveal how deeply human beings have felt connected to the stars, and they remind us that science is just one way of exploring meaning. In modern astronomy, the Milky Way is a subject of data and models, but it is also a source of awe. Seeing it from a truly dark sky site can be a life-changing experience, revealing its full sweep and subtle colors. The central bulge glows yellowish, the arms shimmer in silver and blue, and dust lanes slice across like shadows on silk. It stretches overhead like a roof made of starlight. This real, observable beauty grounds all our theories in something deeply emotional, and that emotional connection continues in art, literature, and music. The Milky Way has inspired countless works of creativity, from Van Gogh's Starry Night to modern science fiction. It appears in poems and novels, in films and songs, often as a symbol of vastness or mystery. Artists use it to represent the unknown, the divine, or the future. Science and storytelling often blend here, as imagination fills in the gaps that data cannot. In this way, the galaxy is not just a structure, it's a mirror of our hopes, and hopes often lead us to questions of purpose. When we study the Milky Way, we are not only learning about stars and gas, we are searching for our place in something bigger. The idea that we are made of stardust, that we live in a galaxy teeming with planets, shifts how we see ourselves. It replaces human centrality with cosmic context, while also making our moment feel rare and beautiful. Every discovery about the Milky Way reshapes our self-image, subtly and powerfully. And that reshaping has only just begun. As technology improves, our picture of the Milky Way becomes more detailed, layered, and personal. Space telescopes, AI-driven data analysis, and deep surveys are revealing features we never knew existed. Future missions will map stars, detect planets, and perhaps even image other habitable worlds. Each breakthrough brings the galaxy closer, not in distance, but in understanding. It is as if we are slowly waking up inside a larger story, and we're not finished writing it. In the coming decades, humanity may send probes into the outer solar system that could eventually escape the sun's gravity. These spacecraft would become part of the Milky Way itself, wandering as our distant messengers. Long after Earth is gone, they may still orbit silently through the galaxy. They are small, but meaningful symbols of a species that looked up and dared to reach out. That gesture connects us to every curious mind before us, and to every star we might one day visit. The distances in the Milky Way are vast, but they are not impossible. A future civilization with enough time and technology could travel between stars. It would take patience, cooperation, and perhaps generations of voyaging. But the potential is there, written into the physics of the galaxy. If life can survive long enough, it might become a galactic presence. And that possibility casts today's choices in a new light. Protecting Earth's environment, advancing science education, and fostering peace all matter if we want to become a civilization that lasts. The Milky Way will be here for billions of years, but whether we are part of its future is up to us. We are at the beginning, not the end, of our galactic story. Every discovery we make now lays the foundation for future journeys. And those journeys may begin with the simple act of looking up. Right now, the Milky Way is moving. Our solar system is orbiting the center. The galaxy itself is drifting through space, and dark matter holds it all in a delicate balance. We are in constant motion, even when we feel still. That motion connects us to everything else in the galaxy. From the heart of Sagittarius A to the outermost halo star, we are all part of the same dance. And that dance goes on, whether we watch it or not. When you see the Milky Way in the night sky, you are looking through time and across unimaginable distances. Every star is a sun, every dark patch is a mystery, and every glow is a reminder of scale. It's easy to feel small, but it's just as true that we are part of something enormous. The galaxy is not above us, it's around us. We live inside it, breathe its stardust, and shape its story in return. One day, perhaps, people will walk on planets orbiting other stars and look up at the Milky Way from different angles. The galaxy will look different depending on where you are. Some views may show the arms clearly, others only a faint haze. But wherever they are, those travelers will still be home. The Milky Way will remain their galaxy too, and they might wonder how people ever saw it from only one small world. In that future, Ancient records, books, databases, images might preserve what we saw from Earth. Our photos of the night sky may become treasured artifacts of an earlier time. Just like cave paintings recorded the earliest human views of the stars, our digital footprints may echo across the centuries. What we choose to capture now becomes the memory of the species. And the Milky Way, as always, is our backdrop. Some scientists even speculate that parts of the Milky Way might carry signs of civilizations long gone, artifacts lost to time, messages encoded in light, or ruins orbiting forgotten stars. If intelligent life ever arose elsewhere and faded away, their traces may still exist in the galaxy's vast corners. Searching for such traces is part archaeology, part imagination. It reminds us that we are not the first to wonder, and we may not be the last. The Milky Way has already lived through more time than all of human history combined. It has seen stars born and die, planets form and vanish, and maybe even life flicker and fade in distant places. That history continues with or without us. But while we are here, we can listen, learn, and look deeper. That is the gift of being conscious in a galaxy full of mystery. One of the quietest, most profound facts is that gravity alone holds the Milky Way together. No walls, no wires, just the invisible pull of mass-curving space. That pull keeps the stars in orbit, the arms in motion, and the structure stable over billions of years. It's a simple force with spectacular consequences, and it links every particle to every other across the entire disk. Some stars in the Milky Way are orbiting black holes. These binary systems can sometimes emit X-ray flares as matter falls inward. Such systems help scientists study extreme physics, including how gravity and matter interact near the edge of collapse. They're like natural laboratories scattered across the galaxy, and they remind us how thin the line can be between light and darkness. Some parts of the Milky Way are still largely uncharted, like the far side beyond the center. Because of dust and distance, we see these regions less clearly than others. But radio waves and infrared observations are slowly peeling back the shadows. As we map more of the galaxy, new features emerge. Arms, streams, and clouds we never knew were there. It's like exploring the deep ocean, one sonar ping at a time. In simulations, the Milky Way is a swirl of stars, gas, and dark matter shaped by constant interaction. These digital galaxies are tested against what we observe, helping refine our theories. Computer models show how spiral arms form, how stars migrate, and how mergers unfold over billions of years. They are tools, but also works of art, painting possible futures and pasts. Through them, we glimpse the galaxy in motion. Every time a telescope points toward the Milky Way, there is a chance of seeing something new. A distant nova, a passing comet, an unknown cluster, a strange pattern in gas. The galaxy is full of surprises, and many discoveries come from simply looking and wondering. Curiosity is the most powerful engine in astronomy. And as long as it burns, the Milky Way will never stop revealing itself. In the end, the Milky Way is not just a place. It's a journey through time, through light, through questions and imagination. It holds our origins and our possibilities. It humbles us and elevates us. And as long as we look up and ask, what's out there, the journey continues. And now, as our journey through the Milky Way comes to an end, take a deep breath and let the stars fade gently behind your eyes. You've just wandered through 100 moments of wonder, stories stitched from gravity, dust, light, and time. You've walked beside exploding stars, followed clouds of gas as they breathed new suns into being, and stood at the edge of black holes. You floated through rings of stars, past streams from galaxies long forgotten, and felt the delicate pull of dark matter shaping all that exists. You've imagined Earth from afar as a quiet passenger spinning in a grand spiral of starlight. And now, there is nowhere left to go, except inward. The same gravity that holds galaxies together is pulling you gently into rest. Just like stars move in rhythm with unseen forces, your body and breath are part of a quiet cosmic dance. Let go of everything you've learned tonight, not to forget it, but to let it settle deeper, like stardust falling through the dark. Maybe in your dreams, you'll return to the glowing center of the galaxy, where stars orbit a darkness too dense to comprehend. Or maybe you'll drift among the spiral arms, skimming the light of newborn clusters and ancient suns. Perhaps you'll find yourself on a lonely rogue planet, floating between the stars, watching the galaxy spin in the far distance like a silver wind. Wherever your dreams take you, remember this: the atoms that make you were once part of stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, they all come from long dead suns that gave everything they had to create something new. You are not just in the universe, you are of it. So when you close your eyes tonight, you're not just falling asleep, you're returning to where you began. Let your thoughts slow, let your breathing soften. Let your body rest. The galaxy will keep spinning. The stars will keep shining. And you are safe. You are part of something vast and beautiful. So sleep now, dream deep, and may your journey continue among the stars.